Hello and welcome to the first video of multidimensional calculus for Thanksgiving week. So in this video we are going to talk about flux. So first of all, the flux represents the amount of something going across either a closed curve in 2 dimensions or a surface in 3 dimensions. By the way, in 3 dimensions, calculating flux is just a surface integral, which again was the notes for what was given today on Friday, November 17th. In 2 dimensions, flux can be calculated using a version of line integrals involving the normal vector. So, to calculate flux, we have the integral over a curve of our vector field dotted with the normal vector ds. To calculate the normal vector, we have the vector defined as y prime comma negative x prime. So in other words, what we are going to do is after we take the derivatives, we are going to switch the components and we are going to make the second component negative. For the integral, we have that vector divided by its magnitude dotted with the vector field ds. Now, let's go ahead and let's calculate a flux integral. So, we are going to calculate the flux of the vector field x squared y comma y across the curve parameterized by 3 cosine t, 5 sine t. So, let's start out by setting up our formula. So, our formula for flux is the vector field dotted with the normal vector ds, which the normal vector can be written as normal vector divided by its magnitude. So now, let's calculate the normal vector and then reparameterize the vector field in terms of our curve. So to calculate our normal vector, we take the derivative of the y component, so the derivative of 5 sine of t is 5 cosine of t, and we put it in the first spot of our vector. We then take the derivative of the x component of the curve, 3 cosine t, which is negative 3 sine t. We put the opposite of that in the second spot, so we have negative 3 sine of t. Next, we are going to find the magnitude of that and put it underneath the vector as we are going to compute a dot product. So the magnitude of this vector can be found, just take each of the components, square them, add them together. That gives 25 cosine squared of t plus 9 sine squared of t. Now let's reparameterize the function. Reparameterizing the function gives 9 cosine squared t times 5 sine t, as again we square the x component of our curve, so we square 3 cosine t and multiply by the y component, 5 sine t, and then the second component of the function is just the y component, 5 sine t. Also note, despite the integral not being given specific bounds, our boundary curve is an ellipse involving sine and cosine. That boundary curve closes and repeats every 2 pi radians. So we can assume the limits to our integral are from 0 to 2 pi. Computing the dot product gives us 225 cosine to the third t times sine t plus 15 sine t. That is over square root 25 cosine t, square root 25 cosine squared t plus 9 sine squared t. At this point, it is best to use an integral calculator, as this integral is at best going to be difficult to do algebraically. At worst, I'm not sure if this is even possible to do algebraically. So, using an integral calculator gives a value of approximately 13.48. So, this is the procedure for any calculation of flux across a curve in 2 dimensions. Again, flux across a surface is just a vector surface integral, so the notes from 11/17 can be referenced for that. and for that reason it will not be covered in this video. Now, let's talk about a different way of calculating this. You might recall that we used Green's theorem as a way of turning line integrals into double integrals. So, as it turns out, there is a separate form of Green's theorem involving flux. By the way, the original form of Green's theorem was the line integral of C of f dot ds was equal to the double integral over the region of q sub x minus p sub y. Now, again, recall that for flux integrals, we switched the components of the derivative of the parameterized curve, as well as inserted a negative sign into the second component. So, with Green's theorem, we have a similar effect seen, as now, instead of q sub x minus p sub y, we have p sub x plus q sub y. Again, it remains turning a line integral into a double integral, and the other parts of the procedure remain the same, as we need to redefine the region so that we are talking about a region itself and not a boundary curve. In case you were wondering, we will not be going in reverse for a double integral in this form. To the best of my knowledge, there are not any apparent applications, and given that fact, we're going to stick with just using the flux form of Green's theorem to go from a line integral calculating flux to a double integral. With that being said, let's do a problem involving this. So a case where applying Green's theorem to flux is advantageous is a case where we have a simple geometric shape, preferably a rectangular or triangular region. So in this case, we are going to calculate the flux of the vector field f is equal to x squared for the first component and y to the fifth for the second component over a curve defined as a triangle with vertices 3, 1, 7, 1, 3, 8. To begin this, we need to find the boundaries of this triangular region. So personally, I prefer to sketch it and then define it, and that's what I'm going to do for this problem. Please note, you are never required to sketch a region. It is just a technique that some find helpful, myself included. A sketch of the region is shown. Conveniently enough, this region has one side that is parallel to the x-axis, another side that is parallel to the y-axis, and then a single diagonal line. So the only part of this region that actually needs to be calculated is the diagonal line, which can be done using point slope form. Using either point, in the case of this example, I am going to choose to use the point 7, 1 to do point slope form on. So using point slope form and simplifying, we end up with the equation for the diagonal line of y equals negative 7 over 4 x plus 53 over 4. Looking at this region, vertically we go from y equals 1 up to that line, and that can be our inner integral. We also go from x equals 3 to x equals 7, and so we have the limits for our double integral. So once we have our limits, we need to go ahead and find the derivative of p with respect to x and the derivative of q with respect to y. Doing so, in this case, p is x squared, so the derivative of x squared with respect to x is 2x, and q is y to the fifth. The derivative of q with respect to y is 5y to the fourth. So we can then insert those into the integral. At this point, our result is a double integral in a similar form to what we have solved before. Given that it is late in the course, and at this point there's a reason for us to save our energy for the final stretch, I am going to allow problems like this, similar to what was stated for surface integrals, once these problems are in a double integral involving no vector components, they can be left. So I am okay with this being left as a final answer, given that at this point there are computer programs where this can be inserted and solved routinely. Thank you for watching this video. I appreciate the effort you have put in this course. I want to wish everybody a happy Thanksgiving week and a happy Thanksgiving if you are watching this before Thanksgiving. I will see you all next week. Bye.